We're going to look at conservation of energy. We're going to start with Newton's law that force is equal to mass times acceleration. In our vector world, we're going to say that F is a vector field, actually a force field, and so it's a vector F. Also, we're going to recall that r double prime of t is equal to a of t, the acceleration vector. So, F of r of t then becomes m of r double prime of t, because mass times acceleration is equal to force. Work done by this force on an object along a path c given by r of t, where t goes from a to b, is, as you know, work is equal to the line integral over c of f dot dr, which is equal to the integral from a to b of f of r of t dotted with r prime of t dt. And using the relationship that we already established, f is ma, f can be replaced by that ma. And so the work is equal to the integral from a to b of m times r double prime of t dotted with r prime of t dt. Now we have this integral with r double prime of t dotted with r prime of t, and we're going to doctor that up a little bit. Remember that we have a product rule for the dot product, right? U dot v is u prime dot v plus u dot v prime. And if we translate that to r and r prime, the derivative with respect to t of r prime of t dotted with itself is equal to ultimately 2 r double prime of t dotted with r prime of t. This is a result from a previous section. So back up to our integral, r double prime of t dot r prime of t can be replaced by half of the derivative with respect to t of r prime dot r prime. So we now have that work is equal to the integral from a to b of 1/2 m times the derivative of r prime dot r prime dt. Well, that we can factor m over 2 out of that. We have the integral from a to b, and r prime dot r prime is the same thing as the magnitude of r prime squared dt, and there was a derivative there, right? So now work becomes m over 2 times the integral from a to b of the derivative of r prime of t in magnitude squared dt. And we have an integral of a derivative. Therefore, we can write this result as m over 2 times the magnitude of r prime of t squared evaluated from a to b. And then using the second fundamental theorem of calculus, we get m over 2 times the magnitude of r prime of b squared minus the magnitude of r prime of a squared, and that m over 2 was in front of the whole thing. The result here is that work has an expression that looks like 1/2 of m v of b squared minus 1/2 m v of a squared, rewriting r prime as velocity, v. But physicists will tell us that 1/2 mv squared is kinetic energy. So the work is equal to the kinetic energy at a point B, that would be the terminal point, minus the kinetic energy at a point A, that would be the initial point. And so work is the change in kinetic energy. Now we're going to come back to that expression in a bit. But first we're going to shift gears just a little bit here. If F, the vector field, is a conservative force field, then the vector field F is the gradient of a scalar function f for some f. Again, physicists will tell us that potential energy at a point xyz is P of xyz is equal to the negative of f of xyz. I'd like to point out this P here has nothing to do with the other P's we've been looking at in this section. This P just represents potential energy. And it's the negative of F. Well, that's where we get the potential function name. But if P is the negative of F, and the force field F is del little f, then it follows that the vector field F is equal to the negative of del P. Thus, the work, which we know is the line integral over C of f dot dr, is equal to the negative of the integral from a to b of del P dot dr, which is equal to, by the fundamental theorem of line integrals, the negative of P of r b minus P of r of a, which means that the work is equal to P of a minus P of b. The order is reversed because of the negative that was out front of the whole thing. So work is potential at A minus potential at B. But before, we said that work was kinetic at B minus kinetic at A. Equating these two gives us that work is kinetic at B minus kinetic at A. And that equals potential at A minus potential at B. You can see that this leads us to being able to say that kinetic at B plus potential at B is equal to kinetic at A plus potential at A. Therefore, we get the law of conservation of energy. This says that ultimately the energy is the same at the beginning of the system as it is at the end of the system, but some of the potential may have been, potential may have been converted to kinetic. Overall, though, the energy was all conserved. This is where conservative vector fields get their name, from conservation of energy.